All right, 11.3 is all about polar coordinates. So we're going to take a look at those first couple of examples. I know we did a quick introduction on Wednesday, but we'll do a few conversion problems, and then we'll move into a graphing and one more beyond that before we go into 11.4. So reminder that looking at a polar coordinate, right, rather than having our typical XY plane, we're now kind of looking at concentric circles essentially, and we're allowed to have a direction as we do this. So we'll see points that kind of like spread out or wrap around, or different language that you'll see in this book with these problems, and you'll see more of a flow with it, which is kind of neat, and it can make petals and different things like that. So, here's our grid for polar coordinates with radius 1, 2, 3, 4, etc., with all of our angles going around our circle as we've always had them. Polar to rectangular and rectangular to polar is listed here. X equaling r cos theta, y equaling r sine theta, and then of course the opposite of that would be r is the square root of x squared plus y squared, and tan theta is y over x. So hopefully you did see this in Pre-Calc Excel last year. It's not completely brand new, so I am approaching this as if we're pretty good with it. And if not, I think it's a relatively easy thing to kind of self-review. Figure 3 right here, and point Q was 3, 5 pi over 6, okay? So the couple of examples, just as a quick refresher, that we will look at. Find the rectangular coordinates of point Q in figure 3. So I did just have so it's written as r comma theta, 3 5 pi over 6, and we want to be able to convert them to x comma y's, right? So we know that x equals r cos theta, so therefore we could say 3 cos 5 pi over 6 is also equal to x, and that would come out to be 3 and times negative root 3 over 2, or negative 3 root 3 over 2. We do the same exact thing for our y coordinate. So we have 3 sine at 5 pi over 6, and we're going to have 3 times a half this time, which would be 3 halves. So our equivalent ordered pair in rectangular coordinates is negative 3 root 3 over 2, comma, 3 over 2. Okay. Example 2 is asking us to do the reverse of that. If I give you an x comma y, can you give me an r comma theta, right? So from the same, in figure 4 now, I'm sorry, rough sketch of that. This is my point P now, 3 comma 2, looks nice and normal. It essentially creates a triangle, right? Here's my 3, here's my 2 on the y-axis, and my theta is that interior angle there. So I want to change that to my r comma theta. So P equals 3 comma 2, then r equals the square root of x squared plus y squared, all coming from Pythagorean. So we have square root of 9 plus 4, root 13, approximately 3.6. And tan theta equals y over x, so, which is 2 over 3, or we could say theta equals tan inverse of 2 over 3, which is 0.588. Right? So our r comma theta now in polar is 3.6 comma 0.588. Okay? All right. So examples 1 and 2, quick refresher. As I had said, 3 through 6 were examples that Mr. Reyes says just skip right through their review, and hopefully the textbook is enough to refresh on those if needed. And then we're going to look at 7 and 8 together. So example 7 has titled Converting to Rectangular Coordinates. Identify the curve with polar equation r equals 2a cosine theta, where a is a constant. Okay. So these types of problems kind of remind me of when we were working back in pre-calc, when you have to deal with all your identities, and you kind of have to see it, like, what do I want to force to happen so that I can manipulate things? And in this case, if I have an r equaling 2a cos theta, it can be helpful to create an r squared relationship. So if I multiply this whole thing, I'm doing this because r squared equals x squared plus y squared, okay? Rather than having r equaling the square root. And we also know that x is equal to r cosine theta. So that is my intent behind multiplying the whole thing by r. So that I'm creating r squared equaling 2ar cosine theta. Right? So the nice thing here is r squared is equal to x squared plus y squared. And r cosine theta is equal to x. Right? So it's probably going to come back to you quickly. I can remember going over these problems with my pre-calc plus students last year. You have to kind of find it, right? So there it is. We found it. So now we can move things around. We can complete the square by adding an a squared right, and then this portion is equal to x minus a quantity squared plus the y squared equals some a squared. Remember that a is some constant, right? And in this case, now I have fit this into the equation of a circle with both the radius is a and center at a comma 0. Okay, so this is also a review problem, but it's good to get that refresher. We're looking for the relationship between our polar and our rectangular, so we're always looking for that. Also, a lot of trig identities are going to come in where we have to recall those and use those. So just get that mind back into that gear of what things are going to make this problem a little bit smoother. We're looking to substitute out. Okay. Example 8 that I want to cover is detailed. I just want to do one graphing altogether to make sure that process is okay. And then beyond that, that's something that you should be able to do. It might take more practice, but that's okay. So when you're graphing, kind of like our conversation, I forget, either earlier this week or sometime last week, sometimes thinking about when symmetry comes in can be helpful. It just saves you some time, but it's not like you have to do it, right? You can always plot every single point, or plug in every single point, and then plot every one individually and see that the symmetry, there's symmetry. Or you can make the observation and use that to your advantage. All right? So the instructions here say sketch the, help me, how do I pronounce that? Limaçon. See, I would have gone with a hard C there. Limaçon. Thank you.
It feels French.
Feels French.
Yeah, that's French.
Okay, thank you. R equals 2 cosine theta minus 1. Right? So I can recall, obviously, that cosine theta is periodic. So I can just plot from negative pi to pi as one kind of domain. All right. So I'm going to, step 1, obviously figure out what my points are. Right? Come up with my table of values. So, and it can be helpful to label these when you put them onto polar grid because it gets a lot. It gets messy. So I'm going to label them A through G. So I have a theta. I have my R, which is equal to 2 cos theta minus a 1. And I'm going to just label those. A, B, C, D, E, F, and G. Okay. So because the symmetry is going to occur with the way cosine works, I'm only going to evaluate 0 to pi. And then the reflection naturally will happen. So I'm going to look at 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and pi. Some of them we can do mentally, some of them just go to the calculator, and that's fine. So if I evaluate r at 0, right, cosine at 0 is 1, 2 minus 1, we get a 1. If I evaluate it at pi over 6, cosine at pi over 6 is root 3 over 2 times the 2, so it's a root 3 minus a 1. I've got a decimal number in here because when we go to plot it, it's helpful to know kind of where, in terms of where the radius is, where does it fall. Pi over 3 is a half times 2 minus the 1, you get a 0 there. Pi over 2 is 0, so minus 1, we get a minus 1 there. 2 pi over 3, we're going to have the 1/2, or negative 1/2, which gives us a negative 1, so we get a minus 2. And then we can start to see kind of the other type of mirror image happening with our unit circle. The 5 pi over 6 is going to give us the negative root 3 over 2, so the negative root 3, another minus 1. So instead of a 0.7, we have a negative 2.7, roughly. 0.73 to be a little bit more exact, not that it matters, and negative 2.73. And then at pi, 2 times, 2 times negative 1 minus 1, we get a negative 3.
Is there a reason why you did 7 points, or is it because just like they're easy numbers?
Easy numbers. No, so
Like
7 is not significant.
So could it be like 6 or 8 or?
It sure could be. You definitely,
Nicola, I recommend you do 100, but on the AP.
Yeah, I'll do
100.
100.
No, 7's not some magic number. It just fit for this problem.
Do you think on like the AP, like when you know it's gonna be like it's just a cosine theta, like you could do just like 4 points? Like you can just do like, I don't know, you do pi over 2, you can do pi over 3, and then 2 pi over 3, and then pi.
Usually when they ask you, they're either specific and they say, okay, plot this table, or really just plot enough so that you know what the pattern is. Because every time you're going to be asked to graph, it's for an interpretation. From there, what can you extract from here? So if you don't get enough information later on in the problem, you might end up going back to do more work anyway. So if they really care how many points, they will tell you. Otherwise, it's for your own benefit.
All right.
I think that's a good answer. All right. Step 2 is you want to analyze r as a function of theta, so we can graph r comma theta in a rectangular and see kind of what the pattern is in terms of positive versus negative. That can be helpful. It's not necessarily mandatory. It could be a quick mental check, but just to have a feel that, okay, if I plotted these points as r comma theta on like a rectangular coordinate, right, we would have, with our symmetry, keeping in mind, we would have 0 up here at 1, right? Then our next angle, pi over 6, would be, a positive number roughly here, and then the pi over 3 is the 0, and it obviously keeps on going down. We know what the cosine curve looks like, right? So nothing magical here. Negative 2, and it's going to keep on going, right? And eventually that'll change. And the same thing would happen over here. But the only real observation is we're saying that we're positive, and then we're negative, which we saw in our table of values, obviously. So this is an optional step. Okay. Let me
So are we graphing on the regular
only
y-axis of the polar?
that one was like an XY axis, but using r and theta.
Okay.
Yes, now we're going to do the polar. The book is just suggesting doing that so that you can, again, think about your symmetry, think about your positive, think about your negative. But it's not, you don't have to do that step. The table of values pretty much does show you the same thing. All right, let me get my 1, 2, 3. Okay. All right, so I've labeled enough at this point. I'm going to try plotting now in green, and I'll label the points on this curve in green, and I'll label them with A through G. So point A is at 0, 1. Right, so that means we are right here. Point B is at pi over 6, comma 0.73. About there. Actually, I can zoom in because I've got my table here. Pi over 3 is at 0 again. Well, I shouldn't say again, but at 0. So that's point C. Sorry, Alex. Pi over 2 is down here at -1. Five pi over 6 is at -2. No, I read that wrong. 2 pi over 3, I'm sorry, is at -2. Right, so because it's -2, I got to be over here. Yep, that's point E. 5 pi over 6 is at -2.73 F, and G is pi, and it is at 0. So it starts here, curves around, okay, and the symmetry would reflect over the X. So very, very similar. I'll do the symmetry in yellow. I think you'll be able to see it. So we're there, we're here, 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 and then we're here, and then we are here, here, and here. Okay, I would definitely recommend practicing these a couple of times, making sure you're putting them the right way. But again, it's nice to order them in some kind of sequential order, or use arrows to show the direction that it's flowing in. But we started here, we went up and around, and then we did the opposite, reflected over the x-axis, we went down and around in the yellow. Okay?
Excuse me, how do we know if it's reflected over the x-axis, or is it just always that way?
It's not always necessarily that way, but that happens because of, that's the best way to explain it. Let me see what the book says to explain that. Part of me says that's why I would just test a point or two to find out. But remembering that my cosine is periodic in the sense, and it also is reflective, and I was showing the same reflection across the y-axis there. 11.3. Let me see what the book said.
It's because for cosine, when it's it starts at 0 and it's spread out to two sides,
Yeah,
right? And then the two sides are symmetric. So it's reflective to like over, so on a rectangular plane, it's reflected on the y-axis. So as you spread out, like on the, as you spread on the x-axis, which in this case will be the angles, it's gonna be
Yeah.
like whether you go left or you go right, it's gonna be reflected, right?
yes, that's exactly right. And the other way to think about it, so rectangular we were saying is reflected over the y. I'm sorry, yeah, the rectangular. And then this one is reflected over the x. The other way to say it is that if you did r of theta and you compared it to r of negative theta, you would get your same outputs. Okay, so then the x, the inputs, the x's, and r of theta, that's using your rectangular. To reflect it. For me, Simon, if I was taking this on a test and I had to graph it, I would just plot those points and not depend on the symmetry. I would just say, all right, I've got my 0 to pi. Let me at least do 1 or 2 of the negatives to make sure. And if I got a couple of them, then I would feel comfortable. That's what I would do.
Thank you.
Yeah.
So just to clarify, when
Yep.
you graph a point, if r is negative, you start from the negative side of like the x-axis, or not the x-axis, but
I know it's hard to think about you. Yeah.
so you start from the left side and then you go however much theta is from there instead of the right side.
If r is negative, you start from the,
Like for point D,
okay?
so you would go from the left side where r equals -1 and then rotate pi over 2, right? Instead of doing
+1, right? Pi half,
Pi halves is -1
negative?
because it's 2 cos theta minus 1.
Isn't that just 2 minus 1?
cosine, right?
Oh, wait.
Yeah, it should be 0.
We're good, right? These points are all correct, yeah. To answer Ann's question, let me, I want to make sure that our language is all the same.
Oh, I thought it was sines, cosine. Oops.
Yep, that's okay.
The textbook also says, like, when graphing things with a negative r, you could also say, like, negative r comma theta is equal to r comma theta plus pi, just like that.
Yeah. I'm trying to come up with like the easiest shortcut to phrase it, and I like that one. Thank you, Heidi. I'm just looking at this other thing that I have from before. The angle theta measured in radians indicates the direction of r. We move counterclockwise from the polar axis by an angle of theta. That didn't help. Hold on. When r is negative. Okay, so 11.3 in summary is what we just covered, being able to convert, being able to graph, being able to take an equation written in one format or the other and convert as well. Okay, 11.4. Area, arc length, and slope in polar coordinates. So conceptually, we've done these things, but we've been doing them in rectangular coordinates.
That's it for 11.3?
That's it for 11.3, a simple one, yeah. I wish I could have squeezed it in a different day, but, so 11.4 is new, because we're now doing calculus stuff to polar coordinates. So So conceptually, a lot of the things are similar, formula-based, they're gonna look similar, but they will be a little bit different, so we have to pay attention to certain details. And I will go through those things right now. Okay, so big picture here, if we're talking about area, we're talking about a Riemann sum, right? And back when we started talking about area with the integration process and rectangles, it was all about as the number of rectangles increase without bound, then we are equivalent to the integral. Very similar explanation right here. Here we are talking about regions being divided into sectors. Similarly, if we increase the amount of them or decrease the theta, the d theta, then we are approaching the same concept here, okay? And they're talking about, they're using these angles, beta and alpha, etc., and coming together to get the smallest sliver that we can get so that we are able to approximate the entire space.
All right, I'm good.
Okay, one thing I'm just going to add here, it's written in there. I drew it out a little bit more explicitly just to help explain it to myself. So if we have this curve, we have some r, we have this delta theta, right? Then the area of this is equal to 1/2 r squared delta theta, right? That's something that we've learned back in probably pre-calc, maybe some form of geometry, you saw it as well. So that's what we are looking to integrate, right?
Get a calculator or not on AP?
Yeah, I would presume that all of these would be, the examples that we're about to do, I didn't touch a calculator for. I think it's going to be similar, like the message back in chapter 5 and 6 for these types of things was like, you're either going to be told just set it up, and that would be a non-calculator, so you have to understand what you're extracting and how you're simplifying things, or it would be a free response where a calculator is active and then your decimal answer is appropriate. Okay.
Excuse me, Ms. Rodriguez, would
Yes.
you please zoom in a tiny bit on the area formula? I cannot read that.
I'm going to give you,
Wait, can you go back?
I can go back, I'm sorry.
For these problems,
This one, this is the one that you want. The other one was just kind of built into the proof.
Okay,
No, I'm
thank you
sorry.
very much.
Yeah.
The
With the Riemann sum and the summation notation, you don't need that. You need this. So area and polar coordinates, f of theta. If f of theta is a continuous function, then the area bounded by a curve in polar form r equaling f of theta, and the rays, alpha and beta, with alpha less than beta, is equal to 1/2 that integral of r squared d theta, or 1/2 the integral f theta squared d theta. So that is of a singular function. We will also do them where there are two. So we need to figure out kind of like that top bottom idea, right left idea, right? Which ones are we subtracting? Just, right here under it, little r equals r is a capital R defines a circle with a radius big R. So by equation 2, the area is equal to 1/2 integral 0 to 2 pi big R squared, which would antiderive and give us a result of pi r squared as expected, right? So it proves the area of a circle formula. As in the previous section, we proved our arc length for our circumference. So example 1, use theorem 1 to compute the area of the right semicircle with equation r equaling 4 sine theta. So I'm going to give you the sketch for what this one looks like. It wouldn't be a bad idea as you're going through your notes to go and sketch it on your own to see if you can get it as well, just as quickly. But in polar coordinates, the language that's used is r kind of sweeps out. If we look at pi over 6, pi over 4, pi over 3, 5 pi over 12, all of those angles that are in there for the r equaling 4 sine theta, you would get a picture that looks like this. And that's not very symmetrical. All right, well, imagine that to be a nice pretty circle with pi over 6, 1, 2, 3, 4. All of these angles falling in here. Pi over 6, pi over 4, pi over 3, and I threw in a 5 pi over 12 and a pi over 2. So that is the graph. I stopped where I did because it is saying the semicircle, the right semicircle. So that's only over there, okay? So I have enough angles to know what my limits of integration are going to be with respect to theta. Okay, so then I have my formula based 1/2 integral 0 to pi over 2, my r squared, which I'll fill in a second, d theta. So based on the formula, that's what I've got. All that I'm doing now is filling in my 4 sine theta for my r. So that gives me a 16 sine squared. So I'm recalling that sine squared is equivalent to 1/2 1 minus cos 2 theta. Think about your identities and think about the ones that are very easily integrable, right? I don't want to have a u sub or a chain rule if I don't have anything to work with. So if I substitute that, I can integrate cosine 2 theta no problem with my linear chain rule. Alrighty? So now this is equivalent to, remember the 4 gets squared, 2, so that's a 16. So I really have an 8 out in front, 0 to pi over 2. And I have inside a 1/2. I could put the 1/2 with the 8 as well. 1 minus cos 2 theta, d theta, which antiderives, integrates to, all I have to...
Wait, when you move no.
Good? So cos 2 theta, cos goes back to a sine, divide by the 2 for the linear chain rule. The 1, also don't forget about that thing, becomes a theta. Okay? So I have a 4, the 8 and the 1/2 come together, theta minus sine 2 theta divide by 2 from 0 to pi over 2. Okay? F of b minus f of a will give me 4 on the outside of everything. Evaluating by plugging in pi over 2 first.
Why can't you move like the 1/2 out?
I did. I didn't write it, but when I anti-derived it, I did.
Oh, yeah.
I just went to a 4.
So you're only anti-deriving 1
I'm
minus
only looking
cos.
at this. Yes. Okay, plugging in pi over 2 to theta minus sine 2 times pi over 2, so sine pi, so that's 0. So we have a 0 there, I don't need it. Minus, if I plug in a 0, I have a 0. A sine 0, I have zeros everywhere. So I end up with 4 times pi over 2, or 2 pi. Okay, is the area over there.
Where did the cosine 2 theta come from?
A trig identity.
Or does that say 1/2 1 minus cosine 2?
It does.
theta?
1/2 times 1 minus cosine 2 theta. Yes.
Should we just know them by the top of our head?
Yeah, I'm just the messenger. Sorry.
Is there like a anything like a